All right, welcome back. We are on to Weber's Law. Basically, to perceive as different, two stimuli must differ by a constant minimum percentage. And as far as that's concerned, things like two lights must differ by an intensity of 8%. Two objects must differ in weight by 2%. And two tones must differ in frequency by only 0.3%. So this is saying that it's not a constant number that's always going to be the same. Like probably the easiest way to think of it is weights. If you're lifting weights and you start off lifting, let's say you're bench pressing and you're bench pressing just a bar, 45 pounds. To add 10 pounds to that is a lot of what you'll notice the difference. You will feel the difference immediately, okay? Whereas if you're lifting weights and you already have 225 pounds on the bar, if you just put 10 pounds on, you may not detect it, okay? I'm not saying you wouldn't have trouble lifting it. I'm just saying you may not detect it. And maybe it's easier to say something like your hands. Okay, if you had a amount of weight in one hand and you were adding to another, it would have to be a difference of 2% for you to notice a difference. Okay. All right. So, and then that's the same for light intensity as well as tone frequency. All right. Sensory adaptation. All right, diminished sensitivity as a consequence of constant stimulation. I love this definition. All right, we adapt to our environment constantly, and the best example of this, and I know we've all gone through this, but when you wake up in the morning and you first put on that T-shirt, and you feel that freshness of the T-shirt, it doesn't last but maybe a couple of seconds. And then you don't think about your T-shirt. It's over with. You're wearing it for the rest of the day until somebody like me brings it up. Or it could be a ring on your finger when you first put it on, or a watch. Okay, all these things. Your socks. You feel them at first, and then your body adapts to these sensations, and it's not a part of. It's not on your mind anymore. Boy, would it stink if it was the other way around. I mean, I don't want to walk around all day long going T-shirt pressing, socks are on, or you have a watch, you have a watch. That would get really annoying. So it's a good thing that we have this sensory adaptation. All right, here we have another example of sensory adaptation, and this has to do with stabilized images on the retina. You can see here the pictures in the book as well on page 198. And here, they're not impaling this person with, I don't know, it looks like a syringe or something in the eye. What it is this is an experiment done where they were trying to figure out, if sensory adaptation is something that's consistent, why then when we stare at something, whether you're staring at each other, at this screen right now, why doesn't the image then disappear? Because if you become adapted to it, shouldn't the stimulus stop working on your sensory devices, in this case, vision? And what they were curious about was, well, is that what happens, or how does it happen, or why doesn't that happen? So they came up with a contact lens right here, you can't see it, that's attached to this, basically a projector, for lack of a better way of putting it, and this tube that comes off of it, and all that is it goes to a computer or some device that allows them to project different images to the eye. What they were trying to find out was why don't things disappear on us all the time? And what they found out, basically, to make a long story short, was our eye is always twitching. It's a constant twitch of our eye, and that muscle movement alone, that twitch, is what allows our eye to constantly reset. It keeps everything sort of stabilized in our environment for us not to adapt to it and then thus have it disappear. What they were able to do with this contact lens is move the picture around that the person was seeing with the twitch of the eye. So what would start happening is the eye would never reset. And basically, they would have a picture of a head here that would start disappearing. The back would disappear, and the front would be there, or the bottom and the top would be there, and so on. It would just go through all these different phases. And you can see there's the triangle that would be missing legs, and so on and so forth. And the reason that would happen is because the eye was not being allowed to reset itself so that the new stimulus coming in would be novel stimulus, new stimulus, and therefore the eye adapted to the situation and the picture started to disappear. Pretty cool, pretty in-depth. You know, it took an interesting person to think of this, to think that they could do that to a contact lens. I know I wouldn't have thought of that. All right. All right, we're gonna move into this section now of the book that has to do specifically with vision. And a lot of these are just going to be terms coming up here that you may or may not have heard of before if you've had physics class or maybe biology. You might have heard these before, and I'm just going to repeat them a little bit here. If you don't understand again, please come ask me. Transduction is the conversion of one form of energy to another. Again, light energy entering your eye. How does it get transformed into something your brain can interpret? Insensation, transforming of stimulus energies into neural impulses, which is what I just said, so I'd like to repeat myself. Wavelength, the distance from the peak of one wave to the peak of the next. So when we're talking about the different energy sources, they sort of come in waves. And when we talk about wavelength, it's the distance between one peak and another peak. Okay, I'll be able to show you better in a picture here in a moment. Hue is the dimension of color determined by the wavelength of light. So hue, the hue of a color, is determined by wavelength, which again I'll show you in a minute. Intensity, the amount of energy in a wave, is determined by the amplitude, okay, or the brightness or the loudness of something. Okay, and again I will discuss what intensity is. Here we have a picture of the spectrum of electromagnetic energy. I don't know what you know about this. I'm no super expert on all of this stuff. I just do know that we see a very small range of the possible energy of the electromagnetic spectrum. We can only use a very small percentage of it to see. Okay, and they're showing you the little blow up here, and I'll use my cursor here to show you how we see purple to blue to green to yellow to red. It's like purple reddish again, but that is something that our eyes are specifically designed to detect. That is what allows us to survive our environment. Okay, we're not designed to see infrared. Okay, we don't. You know, when they talk about snakes, for instance, they're always talking about how snakes. You know, they sit there and they see the different heat signatures of their prey. You know, the little rodents jumping around. I'm such a little small rodent. Oh, look how happy I am! And of course, they always show the snake just sitting there. And then like on the Wild Channel or Animal Planet, they show sort of like what the snake would be looking, how it would be sensing the little rodent, and it would show all these different heat signatures, and the snake can figure out where it wants to strike based on that. Okay, we as humans, we don't use that at all. Okay, that's not. We've been able to build optics, especially in the military, that allow us to do that. So that when you want to when you go to battle and you want to be able to see where people are moving about at night, you can take these optics and you put them over your eyes and turn them on, and you can see different heat signatures, which of course allows you to hopefully figure out where your enemy is. And then of course you have radar, which we use to detect objects moving about us using the sky. Broadcast bands, these are the things this is how we listen to radio or TV. Now it's cable, so it's not really broadcast anymore by and large most of the time. And then you get the AC circuits, which of course is basically your electrical circuits. You do not want to be touching those. Then you go on the other way, you have the UV rays. So when you hear about them talking about how the UV rays are bad for you, and they are, it's because with this light that comes from the sun, also comes ultraviolet rays, which we can't detect, can't see it. We just know it's there when, for instance, we're out on the beach in a hot summer day, and it just, everything makes your eyes, you know, if you're not wearing sunglasses and your eyes, you kind of walk around squinting, and you feel like, why, you know, almost you get a headache, or maybe you're like, why is it so bright? It's so bright I can't even just see people, even though the day is beautiful, there's no clouds out, you know, and that's called ultraviolet light, and our eyes are not very good at taking that in, and it actually can damage our eyes. And so, of course, whenever you want to go out to the beach, we put on the sunglasses that hopefully block out, push away from our eyes a lot of the ultraviolet rays that would cause damage. Okay. Then, of course, we look through the human body through X-rays, and you know, those again are very powerful. Don't want to get a lot of those. The human body can only absorb so much of it before it starts to break down. And it's breakdown, again, coming back to, everybody loves to talk about X-ray. You're going to become a zombie, or you know, you're going to grow a second head out of your neck. No, it's that your organs start to fall apart. Okay, they stop functioning. Gamma rays. Now I don't know anything about gamma rays. Those are supposedly out in space. I do know that in order to become the Incredible Hulk, right here, you do need some gamma rays. Okay, do need some gamma rays. If you wish to become the Incredible Hulk, you can seek that out on your own time. Moving on. Here we go with those pictures of what I was talking about before. With first of all, let's go with short wavelength equals high frequency. So here we have peak to peak. So these are the wavelengths. High frequency, this is where you have bluish colors and high-pitched sounds. Okay. Now, if you have longer wavelengths, see how this distance from peak to peak is greater, you're going to have a low frequency, reddish colors, and low pitch sounds. Okay. Now, when we talk about amplitude, we're talking about from peak to bottom. Okay. How far is that distance? And this will control the bright colors and loud sounds. Loud. Okay. Small amplitude. These would be duller colors and softer sounds. And so the distance between the peak and the base is much less. Okay? If you have questions, please ask me. I hope I was clear. Now we're just going to talk about the parts of the eye. And a lot of this you should probably know. What a pupil is. This is the adjustable opening in the center of the eye. Okay? It's the black dot that is actually allows the amount of light that comes in. So as the pupil gets bigger, more light comes in. As it gets smaller, less light comes in. Iris is a ring of muscle that forms the colored portion of the eye around the pupil and controls the size of the pupil opening. So the iris is actually what is creating this effect on the eye. Okay. Lens is a transparent structure behind the pupil that changes shape to focus images on the retina. So it's kind of like shaped like a cup, and it can kind of stretch. You know, if you're looking at it from the side here, if this was clear and therefore a lens, that's what would allow you to change your focus. Okay. Here we have a picture of the eye, and again, it's showing you all this stuff, which I'm sure most of you have seen before. The big thing here that you want to know is that, believe it or not, all the images come into our eyes upside down. Okay, or they come right side up, but our lens flips it over, and it's first interpreted by our brain as upside down. Okay, our brain has to then flip it back right side up so we can operate in what is a normal environment for us. Okay, so that's why here the light of the candle is like this, and then when you see it in the back of the retina, it is upside down. This part of the eye that comes out and sends the signal to the brain is called the optic nerve. Okay, it is also known as the blind spot. Believe it or not, we all have a blind spot in our eye because, which I'll show you here. There's more. It'll be a better picture in a minute. But because there are no sensory receptors right here, and this actual part where the nerve leaves the eye, there can't be two of the same thing. You know, two things there at the same time. We actually have blind spots. Okay. Some more definitions. Accommodation, the process by which the eye's lens change shape to help focus near or far objects on the retina. So you accommodate as you are trying to focus. Retina is the light-sensitive inner surface. Oh, terrible. That's not how you spell surface. Who did that? Not me. What just happened? Why did it not work? Because I'm using the wrong keyboard, my people. All right, cool. There we go. It's on the inner surface of the eye, containing receptor rods and cones, plus layers of neurons that begin the processing of visual information. So we're going to talk about cones and rods here in a moment. Well, let me go back. Cones and rods, even though I'm sure there's a slide that's coming up in a minute. Remember, cones, C. Cone, C for color. And then the other one, rods, has to be for black and white. It's actually for night vision. Okay? We, as human beings, have lots of cones. That's why we want to operate the day. That's why we're such good hunters during the day. We have great depth perception, all these different colors, just slight shades. Just slight differences in colors mean a lot to us, and we can distance out things and figure out, you know, how to shoot a bow and arrow or a gun at something that, by all intents and purposes, could be camouflage to most other animals. However, we are not the best hunters at night because we are full of cones in here. We have some rods. So after our eyes adapt when the lights go out, we have some rods. And we can see okay at night in the sense that, you know, to walk down the street may not be that bad. But if we were trying to truly hunt at night, it's very difficult for us because a lot of the, because everything is sort of black and white at night, it all blurs together, and so we'll miss stuff. So an animal that may be right in front of us that doesn't move, we may not even see it because, of course, we don't have great noses for hunting. We use our eyesight. But a cat is a night hunter. So when a cat wants to hunt, its eye is full of rods. So when the lights go out for a cat, it's like prime time. It sees the difference between everything out there when the lights are out. So it can really hunt well at night. I'm trying to think, and I'm sure there's a variety of other animals that can do the same thing. But just trying to give you the idea, so for human beings, we are not built for that. And I will stop there for now.